All right, welcome to Unit 2, Lesson 5 on 2D projectiles. In this lesson now, we're going to be taking what we know from combining x and y vectors, and we're going to be applying that again to the kinematic formulas. So now we're not only going to be traveling either straight up or straight down, straight forward, straight back, we're going to have a combination of both x and y vectors combining to create an overall answer. This first example is actually quite good at demonstrating. It's about as basic as any of these questions are going to get. So let's start off on that. It says a rock is thrown horizontally at 27 meters per second off of a 19-meter high building. So we get a little sketch going of this. Let's do something like this. Here is a ledge to a building, and then just ground. And on here, there's a couple values I guess we know. We can say that the height that this thing's going to be falling is 19 meters. 19.0 meters to be more precise. And shooting out from the top, we have a horizontal, and I say horizontal because we're going to have both x and y coming into play here. So we're going to say this is our initial velocity, but in the x or horizontal direction. Okay, that's going to be equal to, well, it's going to be equal to 27.0 meters per second. All right. So I'm going to try to help you conceptualize what's going on here. If we start with a ball at the top here, and it's getting chucked right from the point here, it's going to be moving across the top at a constant velocity of 27 meters per second. In this question, we haven't talked about any air resistance or anything yet. It's not going to slow down whatsoever in the x direction, right? If we had a vector triangle, we could just add that line straight across. In the y direction, though, this object is accelerating because we also have, I'm going to draw my arrow here. Okay, this is going to be initial velocity, vi, in the y direction, up and down. And when it's coming off of a ledge, the only velocity we've given, if you read in the question, is horizontal velocity. So this starts, essentially, it's like we're dropping it, and also it's getting thrown across. So its initial velocity in the y is 0. So as this thing goes on its path, you can imagine a ball falling off of a cliff. Maybe I'll start this a little more horizontal. It's going to start going straight, but it's going to start to accelerate downwards, and it's going to create a curve. It's going to splat down here somewhere. Okay, well, really, that's what the question is asking us. The question is asking us to determine this displacement here. So this displacement is equal to what? This is the displacement in the x. Okay. So with that in mind, we can split this question up, sort of like we've been splitting things up in past lessons. Never quite this elaborate, but we can solve for variables in the y direction. So y variables. We can also set this up for variables in the x direction. So x variables. Okay. Let us start with the y. So in the y direction, we have a kinematic situation. We're essentially doing a question where we're dropping a ball off of a ledge. Okay, so let's set this up here. our initial velocity, 0. So VI in the y is equal to 0 meters per second. Our displacement in the y is equal to 19.0 meters. Okay, that's how far it has to fall. What else do we have in the y direction? We've got acceleration. Acceleration here is equal to 9.81 meters per second squared. I used my displacement. This thing's going to fall a total of 19 meters. It's 19 meters down, but I made it positive. So that means in this particular problem, I'm saying that down can be positive, which means that if anything ends up being up, it's going to be negative. It just makes my math a little bit cleaner. I don't have any negative signs in there. Okay, and finally, right, you may ask, since we have our 3, what do we want to solve for? Time or VF? Well, I didn't totally set up my x variables yet. So I'm going to say for now, this is what we want. Okay, and the VF and y. So the velocity that this thing hits the ground at is going to be, well, we don't really care. And I'll explain this briefly when I get back up here. Let's go into the x variables. So we have an object that's going to be moving constantly sideways, and nothing's going to be slowing it down. And what we want is we want to solve for the time so we know how far or how long this thing can move across at this rate before colliding with the ground. So it's moving across constant speed. The reason it curves down is because the y velocity, it starts to drag it down. So this is going to be a simple case of distance is equal to velocity times time. And we know the velocity already because the VIX is equal to 27.0 meters per second. Time we need to solve for. Okay. Well, let's do that. We need to find what formula is going to work in this place. The formula that is excluding final velocity. The formula I found for that, let's do this in a different color, was displacement, and I'm going to put little y here. Displacement in the y is equal to VIT and that was VIYT plus 1/2 AT squared. Perfect. Now the VI in the y right here was 0. So this value we can essentially cross out. We can say that delta D in the y is just equal to 1/2 AT squared. Excellent. Okay. Now I have a cat trying to walk on me. Go away, cat. Yes, I'll give you attention in a second. Okay. We have 1/2 AT squared. So we can fill that in. No, we have to rearrange first. Sorry, this cat is being very distracting and I lost my train of thought. Let's rearrange this formula. Solving for t here. So we're going to rearrange here. So we're going to have 2 delta dy over a is going to equal to t squared. So t will equal to square root of delta dy, or 2 delta dy over a. Okay, so now we have time is equal to square root of 2 times our displacement value, which was 19 meters, over 9.81 meters per second squared. All right, and that gives us a time of 1.968 seconds. Okay. So the time, time is a nice thing that in both directions is going to be the same. Time isn't a vector value, time's scalar. So the time that it takes for this to crash here is the same as for this to crash here. So this time value can be used down here. We can say that this is equal to the 1.968 seconds. I hope that makes sense to you. Okay, let's move on. So part 2, now that we've solved our time value, we can plug it into this x variable to see how far this thing moves in the x before it's colliding down to its demise. So d is already equal to vt, and so we can plug in values. 27.0 times 1.968 seconds. So to me, this worked out to 53.1 meters. And that is our final answer. 53.1 meters, as if this thing is falling and flying across simultaneously. It will travel that far at a constant rate before colliding with the ground. All right,